You would not explode. You would not freeze instantly. And your blood would not boil like a pot of water on a stove. That's the part nobody tells you. The real version of what happens to an unprotected human body in space is faster, stranger, and somehow worse than anything the movies ever showed you. This isn't trivia. This is the exact set of facts engineers had to get right before they ever let a single human leave a sealed capsule and float in open space. Because get even one of these wrong, and there's no second attempt. You've probably heard the number before, 15 seconds. Sometimes people say 10. That part is roughly true. But almost everything you think fills those 15 seconds is wrong. So let's go through it. Fast. In order. No suit. No air. No warning. There's no countdown clock you can see ticking down, and no warning light blinking before it starts. There's no slow buildup. The moment the pressure goes, everything starts at once. In your lungs, in your eyes, in your blood, in the same second. First myth, explosion. Forget it. Skin does not pop like a balloon the moment pressure disappears. It swells. It strains hard against itself. It does not burst. Your body is tougher than the worst-case version Hollywood has been selling you for decades. Second myth, instant freezing. Forget that too. Space isn't cold the way a winter night is cold. Cold air steals your heat fast because it's physically touching you. Billions of molecules in constant contact, dragging warmth off your skin. In a true vacuum, there's nothing there to touch you. No molecules, no wind. Heat can only leave your body one slow way: radiation. The same mechanism that lets sunlight cross millions of kilometers of empty space to warm the Earth. Slow, not instant. You would not freeze solid in a second. You'd simply start losing heat with nothing left around you to slow it down. Third myth, your blood, boiling like soup left too long on a stove. No, blood is sealed, pressurized, held inside vessels that your own body keeps squeezed shut. That internal pressure doesn't vanish just because the pressure outside your skin did. So if it's not an explosion, and it's not instant ice, and it's not your blood turning into a pot of boiling water, what actually happens to you first? Pressure. Gone, immediately, completely. Every cell in your body has spent its entire life being squeezed by Earth's atmosphere. Roughly 1 kilogram pressing on every square centimeter of you, every second, your whole life, whether you've ever noticed it or not. You've never felt it because you've never lived without it. The instant that pressure disappears, your body has no idea what to do, because it was never built with an off switch. Your first instinct will be to hold your breath. Don't. The air already inside your lungs wants to expand violently now that nothing outside is pushing back against it. Holding it in risks tearing your own lung tissue, the same overexpansion injury that kills divers who panic and hold their breath while ascending too fast. Letting your breath out, as wrong as that feels, is the only thing actually protecting you in that moment. At the same time, your ears would feel the pressure drop instantly, the same way they pop on a descending plane, but far more violent. And any moisture on your skin or in your mouth would already be starting to behave strangely, fizzing faintly at the edges of anything wet and exposed. Now the clock. In 1965, a NASA technician named Jim LeBlanc was inside a vacuum chamber testing a prototype spacesuit when his air hose came loose. The chamber dropped to near vacuum. He didn't explode. He didn't freeze. The last thing he remembers, right before he lost consciousness, was the saliva on his tongue starting to boil. Not from heat, but because the pressure around it had dropped so low that liquid at body temperature could boil at ordinary room temperature. The same basic reason water boils faster on top of a mountain than at sea level. He stayed conscious for somewhere around 10 to 15 seconds. Then his brain, starved of oxygen almost instantly, simply switched off. He was repressurized in under 30 seconds. He woke up fine, completely fine, 10 to 15 seconds. That is the entire window you get to even understand what's happening to you. Not pain, barely panic. Just a fast, quiet fade to nothing. And then either rescue or nothing left to rescue. None of that. The pressure loss, the lungs, the 10 seconds, was space attacking that technician. Space never reached out and did anything to him. It just stopped letting Earth do something for him. Anyone watching from outside, through a window or a camera, would have seen almost nothing dramatic in those first few seconds. No flash, no violent reaction. Just a person who, within moments, simply stopped moving. The most ordinary-looking emergency imaginable, hiding the most extreme set of conditions a human body can be put through. That's the idea this entire video is actually built on. So let's sit with it for a second before we go any further. Space doesn't need to attack you. It only has to remove Earth. It's the difference between someone attacking you and someone simply unplugging the machine that was quietly keeping you alive. The first needs force. The second only needs absence. Think about what that actually means. Every single day of your life, something has been quietly working for you, around you, without ever asking for credit. It has been pressing on your skin. It has been pushing breathable air into your lungs. It has been keeping your blood contained, your sweat useful, your temperature inside a range your body can actually function in. You never had to think about any of it, because it was never not there. The moment you leave that protection without a suit, you don't enter a war zone. You enter a withdrawal, sudden and total, of everything you were never grateful for, simply because you never had to be. So let's slow down and actually look at why each of those 10 seconds happened the way it did. Because the mechanics underneath are stranger than the headline number. There's a specific altitude where this transition starts, even before you technically leave the atmosphere. A line scientists call the Armstrong limit, somewhere around 20 kilometers up, named after a U.S. Air Force physician who studied exactly this danger decades before anyone walked in space. Back when the only people facing it were high-altitude test pilots, pushing aircraft higher than pressurized cabins of the era could safely handle. Above that line, air pressure has dropped so low that water boils at normal body temperature. Not because anything got hot, but because pressure, not heat, decides whether a liquid stays liquid. Pilots flying without a pressurized cabin above that altitude are trained to treat it like the edge of a cliff. Cross it unprotected, even briefly, and your body starts behaving as if it were already in deep space, even with a thin wisp of atmosphere still technically above you. Space, biologically speaking, doesn't begin where the stars look close. It begins the moment pressure drops below what your body needs to keep its fluids the way they're supposed to be. This is also where a common question quietly falls apart. Couldn't you just take one huge breath beforehand and hold extra oxygen for longer? No. The extra oxygen a single breath gives you is small compared to what your brain burns through in seconds. And as you already know, holding that breath in a vacuum does far more harm than good. The limiting factor was never how much air happened to be stored in your lungs. It was always pressure. The same pressure that lets oxygen actually do its job once it reaches your bloodstream. Take pressure away, and extra air in your lungs doesn't buy you meaningful time. It just becomes one more thing working against you. It's also worth knowing that the vacuum astronauts work in near Earth isn't a perfect, total emptiness. Low Earth orbit still holds an incredibly thin wisp of atmosphere, just enough to create drag on spacecraft over years, though nowhere near enough to be breathable or to change anything we've covered here in any meaningful way. True deep space, far from any planet, is closer to a genuine vacuum, but for an unprotected human body, the practical difference between near vacuum and true vacuum is irrelevant. Both remove the one thing your body actually needs: enough pressure and oxygen to keep functioning. That's also why the blood boiling myth is wrong in such an interesting way. Boiling soup on a stove is sitting in open air, exposed, with heat doing the work of turning liquid into gas. Your blood vessels are nothing like that open pot. They're a sealed, closed loop, kept moving by your heart, contained by tissue that's elastic and strong. It's closer to a tightly sealed bottle deep underwater than an open cup left on a counter. The bottle holds its shape and keeps its contents liquid in conditions where an open container of the same liquid would behave completely differently. What does happen, and this part is real, is that any fluid directly exposed to the vacuum, saliva on an exposed tongue, moisture on the surface of your eyes, can start to vaporize almost like a fast, cold simmer. Not from heat, but from the total absence of pressure holding it in liquid form. That's local. That is not your entire bloodstream turning into a pot left on a stove too long. Your eyes would be one of the first places you'd actually feel something. The surface of the eye stays moist thanks to a thin layer of fluid that depends on stable pressure around it. And in a vacuum, that layer can start to evaporate quickly, blurring or distorting vision within seconds. Not from injury, but simply because the eye, like everything else exposed directly to the vacuum, was built to operate at a pressure that's no longer there. The swelling is real too, just not in the way films imagine it. This is the same family of injury that scuba divers fear when they surface too quickly from a deep dive, a condition known simply as the bends. Nitrogen that was dissolved harmlessly in their blood and tissue under high pressure suddenly has nowhere to go as that pressure drops, forming small bubbles in joints and blood vessels that cause real pain and, in severe cases, real injury. A vacuum exposure produces a more extreme version of that exact same physics, just compressed into seconds instead of minutes. This is also exactly why astronauts spend time breathing pure oxygen before a spacewalk even begins, sometimes for an hour or more, deliberately flushing nitrogen out of their blood and tissue ahead of time, so there's less of it left to form bubbles once they switch into a suit running at lower pressure than the spacecraft cabin around them. It's a preventative version of the same problem divers manage by ascending slowly. You can't outbreathe the danger entirely, but you can shrink it in advance, if you know it's coming and have the time to prepare for it. Combined with the loss of outside pressure entirely, this causes real, visible swelling, possibly close to doubling in certain exposed areas. But skin is remarkably tough. It's a living, layered tissue, woven with collagen and elastin fibers built to flex, stretch, and bulge instead of crack. A rigid container under sudden pressure change shatters. A flexible one strains and holds. Your body, by sheer biological luck, is built far closer to the second category. The cold works on its own strange logic too. In true vacuum, there are no molecules around you to conduct heat away, and no wind to carry it off. So the only way you lose heat is through radiation, the slow way. The same way a fireplace warms a room from a few feet away without anyone touching it. It's the same principle that makes a good thermos work. The vacuum gap between its inner and outer walls has nothing inside it to conduct heat away, so the coffee stays hot for hours, leaking warmth slowly through radiation instead of losing it instantly through contact. Your body, exposed to the vacuum of space, sits in roughly that same kind of gap, just on a far larger and far less forgiving scale. But if you're in direct sunlight, that slow logic gets split in half. The side facing the sun can heat up intensely, while the side facing only the black emptiness of space loses heat into that emptiness almost unopposed, at the same time on the same body. It's a bit like standing with one hand inside an oven and the other inside a freezer simultaneously, except it's the front and back of your entire body, with no atmosphere there to blend the two extremes together the way it does constantly here on Earth. Spacecraft orbiting Earth deal with this exact problem every single time they cross from sunlight into shadow and back, with surface temperatures on opposite sides of the same structure differing by well over 100 degrees at any given moment. There's also a danger in all of this that has nothing to do with pressure, heat, or air: radiation. On Earth, you're shielded twice over, once by the atmosphere itself, which absorbs and scatters huge amounts of incoming radiation before it ever reaches the ground. And again by Earth's magnetic field, which deflects charged particles streaming from the sun around the planet instead of through it. Step outside both of those shields, and your body is suddenly exposed to a level of cosmic and solar radiation that took two separate planetary-scale systems to block in the first place. It's not something you'd feel in the first 10 seconds, the way pressure loss is. It's a slower, cumulative danger, one that matters far more on a 6-month trip to Mars than in a sudden vacuum exposure. But it's one more item on the long list of things Earth has been doing for you that has nothing to do with the ground under your feet. And underneath all of it, something else disappears completely. Something so constant in your life you've probably never once consciously thanked it. Sound. Sound needs a medium, molecules bumping into other molecules, to carry a wave from one place to another. In a true vacuum, there is no medium. You could scream as loud as you're physically capable of, and it would die within inches of your own mouth. Not an echo, not a fading signal. Total, immediate silence. The kind that tells you, more clearly than anything you could see, that you're in a place that was never built to carry information about you to anyone else. Think about how much of your everyday sense of safety quietly depends on sound, without you ever crediting it for that job. The crunch of gravel behind you, the hum of an engine approaching, your own voice calling out, reaching someone close enough to help. All of it depends on air being there to carry the wave. Take the air away, and you don't just lose the ability to talk to someone next to you. You lose an entire channel your body has always used, automatically, to understand the world around it. It's also why every word an astronaut speaks during a spacewalk has to travel as a radio signal instead of an ordinary sound wave, converted into an electromagnetic transmission that can cross the vacuum just fine, then converted back into sound only once it reaches another human ear, sealed inside another helmet. The silence outside isn't an inconvenience engineers work around quietly. It's a fundamental property of the environment that has to be re-engineered from scratch, every single time, just to let two people standing a few meters apart hear each other at all. Now here's where the size of the problem really becomes clear. Because everything you just heard about, the pressure, the swelling, the cold, the silence, is exactly why a spacesuit is not clothing. A real spacesuit has to hold a pressurized environment around your entire body, because your body cannot survive without one. It has to supply oxygen continuously, because there's none outside it. It has to manage temperature on both extremes at once, often using tubing that runs water against your skin to pull heat away with real precision, because radiating heat off naturally isn't nearly controlled enough. It has to let you communicate, because sound can't travel outside it. It has to shield you from micrometeorites and radiation. None of that is an accessory. It's a complete, self-contained, miniature version of everything Earth's atmosphere and gravity well were quietly doing for you your entire life. A spacesuit isn't something you wear. It's a tiny Earth, built small enough to fit one person, carried wherever that person goes. Look at what's actually layered inside one, and the comparison only gets stronger. There's an inner layer against the skin for comfort and moisture. There's a network of thin tubing carrying water around the body to pull away excess heat. The same basic idea as a car radiator, just shaped to fit a human torso and limbs. There's a pressure layer, an airtight bladder holding the suit's internal atmosphere stable. There's an outer layer built from multiple insulating sheets reflecting heat in both directions, keeping the sunlit side from cooking you and the shadowed side from draining you dry of warmth. And wrapped around all of it is a tough, woven outer shell, built to resist exactly the kind of micro-impacts that would otherwise puncture everything underneath. Each layer exists because Earth was quietly doing that exact job for you your whole life, and none of them can be skipped once you leave it. That cooling system matters more than people expect, for a reason that sounds backwards at first. Astronauts on a spacewalk are far more likely to overheat than to freeze. Floating in the vacuum doesn't slow a working human body down. Physical exertion inside a pressurized suit, gripping tools, bracing against a structure, moving against the suit's own resistance, generates real metabolic heat with nowhere for it to go through the slow process of radiation alone. Without that water-cooled garment running underneath everything else, an astronaut working hard during a 6-hour spacewalk could overheat dangerously, even surrounded by a void that on the shadowed side is colder than almost anywhere on Earth. None of that complexity comes cheap either. A modern spacewalk suit can weigh well over 100 kilograms on Earth, though that weight stops mattering once it's in orbit, and can cost tens of millions of dollars to design, build, and certify safe enough to trust a human life inside for hours at a time. Every layer, every seal, every redundant system in that price tag exists to replace something Earth was providing you for free, automatically, your entire life, without ever sending a bill. That price also buys something easy to overlook: mobility, which a suit pressurized like a small, rigid balloon naturally fights against. Bending a gloved finger or flexing an elbow inside a pressurized suit means working against the suit's own internal pressure with every single movement, which is part of why astronauts often come back from long spacewalks with sore hands and forearms, not from the work itself, but from hours spent fighting their own life support system just to hold a tool. That same swelling problem nearly ended the very first spacewalk in history. In 1965, cosmonaut Alexei Leonov became the first person to ever leave a spacecraft in orbit. And while he was outside, his suit ballooned in the vacuum far more than engineers had expected, stiffening his joints and stretching the fabric until he could no longer fit back through the airlock he'd just floated out of. With his oxygen running down and no time to consult anyone on the ground, he made the decision himself to bleed some of the suit's internal pressure out into space, shrinking it just enough to squeeze back inside. A move that risked exactly the kind of decompression injury we've already talked about, the bends, in order to avoid the more immediate danger of being stranded outside entirely. He made it back. It remains one of the clearest real examples of how a tiny Earth, however carefully engineered, can still fail in ways its designers never fully anticipated, which flips something most people assume about astronauts on a spacewalk. We call it walking in space, like they've stepped outside, exposed, bare against the void. They haven't, not for 1 second. An astronaut on a spacewalk has never actually touched space directly. They're sealed inside their own pocket of pressure, oxygen, and temperature control at every moment. What looks like a human floating freely through the vacuum is, more accurately, a human-shaped capsule of Earth, moving through a place that would otherwise end them in under a minute, carrying their planet's conditions with them, the way a hermit crab carries its shell. Zoom out from the suit itself, and you'll find the exact same idea at a larger scale. A space station, a capsule, an entire spacecraft, is really just a bigger version of the same trick. A sealed shell engineered to recreate pressure, oxygen, and temperature control for a whole crew instead of one person. The International Space Station holds a breathable atmosphere at close to sea level pressure, scrubs carbon dioxide around the clock, and regulates temperature constantly. For the same reason a suit has to do all of that for an individual astronaut. Every spacecraft humans have ever flown is, in that sense, just another tiny Earth, sized up to fit a crew instead of a single body. Oxygen alone still isn't enough to keep that tiny Earth livable, though. And this is the part almost nobody thinks about until it's explained. Every breath you take inside a sealed suit also produces carbon dioxide. And unlike Earth's atmosphere, a vast, forgiving ocean of air that disperses it instantly, a sealed suit is just you and a small enclosed volume of air. Without active scrubbing, your own exhaled breath would slowly turn that bubble toxic, even while oxygen is still technically present, which is part of why suit and spacecraft sensors track carbon dioxide levels just as closely as they track oxygen, watching the thing your own body produces almost as carefully as the thing it consumes. You wouldn't run out of air to breathe in. You'd be poisoned by the air you'd already breathed out. The early symptoms aren't dramatic either, which makes them genuinely dangerous. A mild headache, a creeping difficulty concentrating, a feeling of being slightly off. The same vague warning signs that build quietly before something far more serious sets in. Easy to dismiss, right up until they aren't. That exact problem became one of the most famous crises in spaceflight history during Apollo 13, when the crew crowded into a smaller capsule than it was built for, and its carbon dioxide scrubbers weren't enough for 3 people breathing into it for that long. Engineers on the ground had to rig a square cartridge to fit a round opening, using cardboard, a sock, and tape, because without it, the crew would have slowly poisoned themselves with their own exhaled breath, in a spacecraft that still had plenty of oxygen left. Even something as basic as sweating stops working the way you'd expect inside that bubble. On Earth, sweat cools you because liquid evaporates steadily off your skin into surrounding air. In a vacuum, with no atmosphere to gradually absorb that moisture, exposed liquid can flash away almost instantly instead of evaporating in a slow, controlled way. Removing one of your body's oldest cooling tools, the moment the atmosphere that tool depends on disappears. This matters more than it sounds like it should, because thermal regulation in space is already a constant balancing act, even inside a working suit. And losing one of your body's own natural cooling mechanisms removes a layer of margin that engineers otherwise have to make up for entirely with mechanical systems. This is exactly why even a tiny imperfection in a suit becomes a genuine emergency immediately, not eventually. A small tear or a micrometeorite impact no bigger than a grain of sand can create a leak. And a leak in a pressurized suit isn't something you deal with later. It's a countdown. Pressure and oxygen start dropping together, and depending on the size of the breach, that countdown could be minutes or far less. There's no slow leak you have time to leisurely investigate. There's only a shrinking window, and the suit's entire design exists to stretch that window as long as it possibly can. Even the helmet visor is fighting its own version of this same exposure. Unfiltered sunlight in space is far harsher than anything reaching the ground through Earth's atmosphere, which normally scatters and absorbs a meaningful share of it before it ever touches your skin. Visors are coated to filter that glare and block damaging radiation, while still letting through enough visible light to actually see by, a balance that has to hold steady whether an astronaut is staring straight into direct sunlight or into the near-total blackness of the shadowed side, sometimes within the same few minutes of a single orbit. That's why suits carry backup pressure layers, redundant seals, and warning systems built to flag pressure drops long before a human could ever feel them. A leak doesn't usually announce itself with a dramatic hiss. It can be slow, quiet, almost unnoticeable at first. The kind of thing you'd only catch because an instrument reading drifted slightly off where it should sit. That's the unsettling part of operating in an environment like this. The danger doesn't always look dangerous in the moment it begins. It just quietly starts a clock. This is also why astronauts spend enormous amounts of time training for exactly this kind of failure before they ever leave the ground. Rehearsing suit checks, emergency procedures, and rapid return to safety routines until the response is close to automatic. Most of that training isn't about advanced science. It's about speed, and about removing hesitation from a situation where hesitation is the one thing you can't afford. Panic also increases oxygen consumption and burns through those last functional seconds even faster, which means the calmest possible response to losing your atmosphere is also the one most likely to buy you a few more usable seconds. The same seconds that can separate a survivable accident from a fatal one. You might assume solid ground changes any of this. It doesn't. The moon has essentially no atmosphere worth mentioning, so standing on its surface without a suit is, for your body's purposes, functionally identical to floating in open space. Mars does have an atmosphere, but it's roughly 0.6% the pressure of Earth's, mostly carbon dioxide, far too thin to keep your blood and bodily fluids out of the same low-pressure danger zone as true vacuum exposure. On the Moon, surface temperatures in direct sunlight can climb past the boiling point of water, while temperatures in permanent shadow just meters away can drop to nearly 200 degrees below zero, sometimes within the same crater. Mars swings less violently, but still spends most of its time far colder than anywhere habitable on Earth, with average temperatures hovering around 60 degrees below zero. A planet's surface is not automatic safety. Pressure is safety. Oxygen is safety. Gravity gives you a direction to fall in. It does not give you a single molecule of breathable air. It also means rescue itself works completely differently depending on where you are. A spacewalk failure near a space station might be resolved by a crewmate just a few meters away, close enough to physically grab a tether and pull someone back inside within the same critical seconds that matter everywhere else in this story. A suit failure on the Moon could mean minutes before help arrives. A suit failure on a future Mars mission could mean there is no help arriving in any meaningful time frame at all, because the nearest realistic rescue option might be an entire planet away. Distance doesn't just make the trip longer. It makes every single one of these dangers far less forgiving the moment something goes wrong. It's worth sitting with that, because it quietly breaks one of the most comforting assumptions people carry about future space travel. The idea that once humans reach another planet, the hardest part is over. That the danger was only ever in the empty stretch of travel between worlds. Landing on the Moon or Mars doesn't end your dependence on a sealed, Earth-like environment. It just relocates the exact same problem to a new piece of ground. The suit doesn't come off when you land. The countdown clock on a leak doesn't reset just because there's dust under your boots instead of stars under your feet. And if you're wondering whether anything actually does handle this better than we do, the answer is yes, just not anything you'd expect. Tiny, nearly indestructible creatures called tardigrades, sometimes called water bears, have been exposed directly to the vacuum of space in real experiments and survived. By shutting their own bodies down into an almost completely dried-out, dormant state until conditions improve again. Humans don't have that option. We can't simply pause our own biology and wait the danger out. Every system that makes you you, your blood, your brain, your breathing, has to keep running the entire time, which is exactly why the 10 to 15 second window matters so much. You don't get to power down and come back later. You either get help inside that window, or you don't. So, after all of that, what's the honest, complete answer to how long you'd actually survive? Roughly 10 to 15 seconds of useful consciousness before your oxygen-starved brain shuts down. After that, unconscious, but not yet dead, with a short window, maybe a minute or two, where rescue and repressurization could still bring you back, with little to no lasting damage. Past that window, the danger climbs fast and permanently. That fade into unconsciousness isn't a violent collapse either, which is its own kind of disturbing. Pilots in training are sometimes put through a controlled hypoxia exercise, breathing reduced oxygen at simulated altitude in a safe, supervised chamber, just to feel what a starved brain actually feels like. Almost everyone describes the same pattern. Not panic, but a strange, creeping fog. Simple tasks get harder. Thoughts slow down. People keep insisting they feel completely fine, right up until the moment they stop responding altogether. Because oxygen deprivation can quietly switch off your own ability to notice it's happening. Aviation even has a specific name for this exact window: time of useful consciousness. The brief period after oxygen drops where a person can still think and act deliberately, before slipping into confusion and then blackout. At high cruising altitude after a sudden cabin depressurization, that window might stretch to a minute or two. In the vacuum of space, with no residual air pressure helping at all, That same window compresses down to the 10 or 15 seconds we've been talking about the whole time. Much of what we actually know about short vacuum exposure and recovery doesn't come from theory. It comes from controlled experiments in the early decades of spaceflight, where brief, accidental, or test exposures, including the one involving Jim LeBlanc, were studied closely afterward, with researchers monitoring heart rate, pressure, and recovery time in careful detail to understand exactly where the line between dangerous and fatal actually sat. Across those cases, the pattern held. Rapid loss of consciousness, measurable swelling, and then, if pressure was restored within roughly a minute to 90 seconds, recovery with little to no lasting harm. It's part of why engineers were ever confident enough to send humans into pressurized suits that, however well designed, are still just one seal away from failure. The evidence said a short, accidental exposure was frightening, dangerous, and survivable, in that exact order, as long as help arrived fast. It isn't one dramatic number. It's a handful of seconds of awareness, a short window of true reversibility, and then a rapidly closing door, all compressed into a timeline that barely resembles any other kind of danger you can imagine. Drowning gives you a minute or two of real struggle. A fall gives you a few seconds of fear before impact. This gives you almost nothing, just enough time to notice, and then none at all. But the number was never really the point. You are not surviving space. You are surviving the sudden absence of Earth. Every thread in this video, the lost pressure, the racing clock, the silence, the heat on one side and the cold on the other, traces back to that one missing thing. Not an attack, an absence. And it's been holding you up, quietly, your entire life, without you ever once having to ask it to.